Hello, everyone. This is Rikhav Shah, and this talk is on a spectral approach to polytope diameter. This talk will have three main parts. The first is an introduction to the problem and a little bit of history. The second will be about results from spectrograph theory. And the third will be how to use those results from spectrograph theory in the context of this problem, using some facts from convex geometry. So let's go to the next slide. So the first thing to note is just what a polytope is. A polytope is the set of points satisfying a collection of linear inequalities, ax less than b, entry-wise. For our purposes, b will be always be a positive vector. That way, 0 is in the interior of this polytope. And given any polytope, you can always translate it so that this is indeed the case. Define a point on the surface of this polytope to be a vertex if d of the constraints of the polytope are tight at that point. And a line segment similarly has d-1 constraints tight at those points. So in this picture here, we have drawn dots for the vertices and lines for the edges, denoting the vertices and edges of the cube, which is, of course, a polytope. The vertices and edges of the polytope become the vertices and edges of a graph called the one skeleton. This graph is always connected, and the problem that we are dealing with is how to bound its diameter. So what is the largest possible diameter of a graph in terms of m, the number of constraints, and d, the ambient dimension? This problem is motivated by linear programming, where these potential solutions are the vertices of some polytope, and various algorithms will try to find the optimal vertex, starting from an arbitrary vertex by jumping between adjacent vertices. So in this picture here, I have a diagram of a polytope, and the red path denotes the path that an algorithm might take to the optimal vertex. So a trivial bound is just the diameter is bounded by the total number of vertices, which is m choose d. But the goal is to do much better. A conjecture from the 1950s is that the diameter of this graph is always less than m minus d, so the number of constraints minus the ambient dimension. It turns out this conjecture is false, but there's a relaxation which we study. But one of the first pieces of, or large pieces of progress, and still today the best piece of progress in the general case toward this conjecture, is that the diameter is upper bounded by m minus d to the log d. So it's significantly better than the m choose d bound on the number of vertices, but it's still a long way to go from the Hirsch conjecture. And indeed, like I mentioned just now, the Hirsch conjecture itself turns out to be false. In particular, a construction due to Santos of these polytopes called spindles show that the diameter has to be at least m, in fact. So the relaxed conjecture, or the updated conjecture, is that the diameter is just some polynomial in m and d. And we can still hope that this is true. There are no lower bounds, or there's nothing disproving this conjecture yet. But similarly, there hasn't been tremendous progress in the general case. So instead, we introduce a new parameter, or there's a parameter that the literature has introduced in order to make progress. And that parameter is the maximum determinant of any submatrix of the constraint matrix A. In particular, the goal now is to bound the diameter in terms not just of m and d, but also delta, this max det. So two of the important results in this area are, one, if the max det is 1, in other words, this constraint matrix A is unimodular, then the diameter is indeed less than some polynomial in m and d. And for larger delta, there's a more recent result which shows that the diameter is at most O of d cubed times delta squared. So this work seeks to make an improvement, or does make an improvement, where the d cubed parameter is improved to a log m delta, or improved in some setting of these parameters. Okay. So that is what this talk will be about. Now on to spectrograph theory. This is the first set of ingredients which are key to the results in the paper. First, I'm going to define this generalized adjacency matrix, which is similar to a regular adjacency matrix, except we allow the off-diagonal entries to be anything as opposed to simply 1. Actually, we require that they be positive. So Sij is only non-zero if ij is an edge of G, and that value is actually going to be positive. And the result about them is that if we have a spectral gap, so there's so in other words, the largest eigenvalue of S, say, is 1 plus gamma for some small parameter gamma, and the rest of the eigenvalues are in the interval -1 to 1, then we say that this matrix S has a spectral gap of gamma, and the diameter is upper bounded by log of the number of vertices plus log of 1 over the smallest entry of the eigenvector corresponding to the top eigenvalue divided by square root of gamma. So the larger the spectral gap, the better bound on diameter 1 achieves. In this picture, I have drawn a little diagram of where all the eigenvalues are. So the lambda n through lambda 2 are all in the interval -1 to 1, and the top eigenvalue is gamma larger than the rest of them. So a proof of this theorem is quite straightforward. First, consider raising this generalized adjacency matrix to the kth power. And note that because S is a symmetric matrix, we can decompose it into its spectral decomposition. And we will write this with its top eigenvalue separated out from the remaining eigenvalues. And from this expression, we can bound each entry of this matrix S to the k, lower bounded rather, quite simply by bounding each term independently. So the first term is at least 1 plus gamma raised to the k times the smallest entry in that in V1 squared, then minus an upper bound on the absolute values of the remaining terms. So each of these other lambdas are at most 1, and VT is each entry there is also upper bounded by 1. So rearranging this inequality and taking k large enough means that every entry in S to the k will be positive. But the entries in S to the k can only be non-zero whenever there is a path from I to j. So because each entry in S to the k is positive, we know that there is an upper bound of k on the diameter of the graph. But of course, in this bound, we see that there's a dependence on gamma as opposed to root gamma on k. And the way to fix this and introduce the root gamma is to replace raising S to the kth power directly by applying the Grigoriev-Chebyshev polynomial to S. So these polynomials are bounded by 1 on an absolute value on the interval -1 to 1, and they also grow really quickly outside that interval. And they grow sufficiently quickly that we only need k to have a dependence on root gamma as opposed to gamma. Okay, so that's the theorem from spectrograph 3, which we require for our main result. And now we need to know how to apply it to this problem. So remember the two parameters that we're going to be working our way towards are, one is a spectral gap, and two, a lower bound on the minimum entry in the eigenvector. So, but in order to do all that, we need to first construct a generalized adjacency matrix, right? We know what the adjacency matrix is, but we need to know what weights do we apply on each of the edges such that we end up with those two desirable properties, a spectral gap and a sufficiently large smallest entry in an eigenvector. So to do that, we're going to introduce the idea of the polar of a polytope. So first of all, think of a polytope, ax less than b, as the constraints are, or think of the rows of this matrix A as the individual constraints. If there are m of them, then there are m facets and n vertices, where n could be quite large. But these rows, we can, instead of taking them to be the constraints, we can take them directly, normalize them appropriately, and then take their convex hull. And that will also produce a convex set. And this convex set is called the polar of P. And the m facets of the original correspond directly to the vertices of the polar, which can be seen just by the definition. These constraints become the point that we're taking the convex hull of. But furthermore, the n vertices of the original polytope become the facets of the polar. And that fact is less obvious to see, but here we've drawn an example. If a cube is some original polytope, its polar will be the octahedron. So the 6 facets or faces of the cube become the 6 vertices of the octahedron, and the 8 vertices of the cube become the 8 facets of the octahedron. So the graph, which corresponds of edges and vertices in the original, becomes a graph in the polar where the nodes in the graph are the facets, And the edges in the graph are the intersection between two adjacent facets. So whenever two facets have a non-trivial intersection, then that produces an edge in the graph. So it's the facet incidence graph of the polar. So the n vertices of the original become n facets in the polar, and we want to bound the diameter of the facet incident graph of the polar. Now the key idea here is that the polar itself is some polytope. So in other words, it could be written in the form mx less than c for some matrix M and a positive vector c. In some neighborhood of that vector c, think of the function which sends that vector c to the volume of the of that polytope. So we've introduced this parameter c, which correctly parameterizes the space of polars, and we are now considering this function which computes its volume. The first claim that we make is that the Hessian of V is indeed a generalized adjacency matrix of the graph, and it will be, or a scaling of it and a shifting of it will be the one which we apply the theorem to from the previous section. And the second claim is that this Hessian has exactly one positive eigenvalue, and this will help us get a spectral gap. But first, let's prove claim one, and we'll just sort of do a proof by picture here. So think of the derivative of this volume with respect to one of those slack variables, say Ci. Now we claim it's equal to the area of Fi. And to see that, look at this little diagram written on the right-hand side of the slide here. As you change Ci by some small amount, the amount of volume that's added to the polytope is that little rectangular region where the length of the rectangle is Fi. So the derivative of V with respect to Ci is just that area. Now, if we were to take the derivative of this function with respect to a different slack variable, say Cj, then we want to know how quickly does the size of one facet change as you change the slack variable corresponding to a different facet. And there you can see that that value will only be non-zero if the two facets intersect. If the two facets don't intersect, then changing C1 is not going to affect the area of Ci, is not going to affect the area of Fj for some different j. So this value is only non-zero, indeed is only non-zero if the two facets intersect. And furthermore, we can exactly compute what the magnitude of the effect is, and it's just the cosecant between the angle of the vectors which are normal to the two facets. Okay, so now let's look at claim two, which is that this Hessian has exactly one positive eigenvalue. And this is actually an instance of a more general fact about log concave functions. So the first claim is that the function which maps C to log of the volume is a concave function. And as a consequence, the Hessian is a negative semi-definite matrix, and then the Hessian of the volume has exactly one positive eigenvalue. Now, these aren't trivial facts to prove, but they're known previously, and we've, for this talk, just take them to be a black box. But this is a general fact that works for any kind of log concave function. So this fact on the previous slide here just says that there's one positive eigenvalue, but it doesn't say how large it is. And we actually want it to be quite large comparative to the other eigenvalues in order to get a sufficiently large spectral gap. And that will be done by noting the Hessian is of this particular form of minus a Laplacian plus a strictly positive diagonal matrix. So when you compute the individual entries, the off-diagonal entries have these dependence on cosecant. It turns out the diagonal entries have a dependence on tangent in sum over all facets or all adjacent facets. So the entries in the diagonal are all smaller than they would need to be in order to, or are all smaller than the sum of the entries of the other entries in that particular row. So the Hessian is sort of like a Laplacian, except all the diagonal entries are wrong, and they're all wrong in the same direction. So we can express the Hessian as minus the Laplacian plus a strictly positive diagonal matrix. So multiplying the left and right-hand side by d to the 1/2, we get by Sylvester's law that the left-hand side has exactly one positive eigenvalue, and the right-hand side is a negative semi-definite matrix, because recall that Laplacians are positive semi-definite, plus the identity matrix. And indeed, both sides of this equation has an eigenvalue at exactly 1, and that's because the Laplacian has a null space. So it's pretty clear how to construct the corresponding eigenvector on the right-hand side. Just take V to be the square root of all the diagonal entries in D. And then all the other eigenvalues are negative or 0, so they're all non-positive. So we would like to do a scale and shift all these eigenvalues, so such that lambda2 through lambda n all lie in the interval -1 to 1, as opposed to -infinity to 0. And that way, and then shift it up so that the top eigenvalue is at 1 plus some parameter gamma, as opposed to being exactly at 1. So we can do that by just lower bounding the eigenvalues far away from 0 using Kirch-Gordon circle theorem. But when you work out what all those things are using a little bit of linear algebra and some trigonometric inequalities, you can find that this gamma parameter, when you scale everything up, is the sine squared of the smallest angle between facets of the polar. And the angle between facets of the polar, what I mean is the angle between their normal vectors. So with this result, we can apply the theorem, the bound on the diameter, using the theorem that used Chebyshev polynomials in the proof. And we also know exactly what V min is. Remember, we said just on the previous slide that V is equal to the square roots of the diagonal entries of D. So we can convert all those bounds into bounds using the angles between adjacent facets, and also use the fact that, and also bounds on the size of the entries in A. And that becomes the desired bound at the end. If one likes, one could instead get a bound not in terms of this max det squared, but instead in terms of the largest entry in A, and also the smallest angle between adjacent facets. But just to make a comparison with other results in the literature more straightforward, we express it here in terms of the delta squared. Okay, so as a summary of what happened here, we started with the fact that the log of the volume of the polar of a given polytope is a concave function. As a consequence, the Hessian of that function has exactly one positive eigenvalue, which implies that using then a relationship with a Laplacian matrix, we can show that that matrix has a sufficiently large spectral gap, such that when we apply a theorem from spectral graph theory, that we arrive at the fact that the graph has small diameter. Okay. That's a summary of these results. And some open questions in the future are, one is, can we prove the polynomial Hirsch conjecture for random polytopes? So we leave the general polynomial Hirsch conjecture is still completely open. And second, can we analyze what happens for a random walk on the graph? So this was analyzing sort of the length of an optimal walk, but what happens for a random walk? And a third question is, can we use some higher Hodge-Riemann relations for polytopes? So the fact that the Hessian has exactly one positive eigenvalue is a Hodge-Riemann relation, but there's a question as to whether, a highly speculative idea as to whether the higher relations could do something as well. That's it for the talk. I appreciate you all tuning in, and feel free to email us if you have any questions or thoughts on these open questions. Thank you and have a great conference.